Hi everyone, I'm Elena Bueno-Benito, and today I'll be presenting our work, CLOT, Closed-Loop Optimal Transport for Unsupervised Action Segmentation, done together with Mariella Dimiccoli. First, let's introduce the temporal action segmentation task. That is, figuring out what action is happening and when it happens in a long, untrimmed activity video. For example, in a video capturing someone making pancakes, we want to identify actions like stirring the dough or pouring milk on the pancakes. Usually, these videos are often long and complex. They can last several minutes, not just a few seconds. The task has typically been addressed in a fully supervised fashion, which achieves the best performance, but it requires manual frame-level annotations, which are extremely expensive to obtain and make the methods not scalable. More recently, weekly or semi-supervised approaches have reduced the annotation cost, but they still depend on some labeled data. In contrast, unsupervised methods, like ours, are completely label-free. The last methods usually jointly learn frame representations and pseudo-labels simultaneously. A recent example is ASOT from CVPR 2024, which uses optimal transport to align frames and actions. However, unsupervised methods still face two key challenges. First, many actions are very short, making them hard to detect. And second, frame-level assignments tend to be noisy, which prevents stable and consistent learnings. These limitations motivate the need for a new framework, one that can handle noisy frame predictions and capture fine-grained temporal structure without any supervision. And that's where CLOT comes in to overcome these limitations. Our goal is to enable the model to discover meaningful actions in long, untrimmed videos of the same activity, without any manual annotations, paying attention to short actions, and avoiding noisy frame assignments. For example, given several videos capturing the activity of making a sandwich, we want the model to automatically identify actions like cutting the bun, smearing butter, or putting a topping on top across all videos. We present CLOT, a method that introduces explicit feedback between frame and segment representations to achieve fine-grained action segmentation. In our approach, the first step learns to assign each frame to a potential action embedding while also enforcing smoothness in time. In the second stage, the decoder takes this frame embedding and produces a segment embedding. Then, we introduce a cross-attention mechanism between the encoder and decoder outputs. And finally, because of this explicit feedback mechanism, the model generalizes across different videos of the same activity. Let's take a closer look at the architecture. These slides evolve gradually, so I'll guide you through them. We start by extracting frame features using a simple pre-trained extractor. Then, we initialize two sets of learnable embeddings: frame embeddings, representing visual observations, and action embeddings, representing potential action prototypes. In the encoder, we use a simple MLP combined with a feature dispatching mechanism. This module assigns each frame to its most similar action prototype using a learnable similarity function. You can think of it as an adaptive routing process that filters out irrelevant or background frames. Next, we measure how similar frame and action distributions are using the sliced Wasserstein distance, SWD. Instead of comparing high-dimensional features directly, we project them onto multiple random 1D directions, sort them, and compare these projections. This captures fine-grained structure efficiently. We solve the optimal transport problem to produce soft pseudo-labels at the frame level. Each frame gets a probability distribution over k possible actions, representing how likely it is to belong to each cluster. In the second stage, we use a query-based attention. Instead of decoding actions one by one, we predict them in parallel using query embeddings as segment prototypes. This avoids error accumulation. Once we have these segment embeddings, we again define an OT problem. This produces another set of soft pseudo-labels, now at the segment level. After decoding, segment embeddings act as teachers for the frames. Through cross-attention, frame features are refined with this segment-level information. In the final OT step, these labels are refined through segment-level feedback. Frames improve segments, and segments refine frames. That's the closed loop in CLOT. This is our training pipeline. The loss is defined as the sum of three cross-entropy terms. Here, P always represents a probability distribution over action prototypes at the frame level, the segment level, or the refined frame level. At the frame level, the loss makes individual frames align with initial pseudo-labels. At the segment level, the loss enforces temporal consistency, so frames in the same segment stay coherent. Finally, at the cross-attention level, the loss refines both embeddings and pseudo-labels, closing the loop between frames and segments. Here we can see qualitative results from the 50 salads dataset. Each column corresponds to a different video, in this case examples of people preparing a salad. And within each column we can follow the evolution of the model's predictions through the loop. From the initial probabilities P, those are the soft frame-to-action assignments, to the final pseudo-labels T, after completing the full cyclic refinement TR. Notice how the segmentation becomes progressively cleaner after each iteration. The cyclic feedback really improves boundary sharpness and consistency. So here we can see what happens when we remove each component of our model. Without SWD, we lose fine-grained feature relations. Without feature dispatching, background and action frames get mixed. Without the parallel decoder, temporal consistency drops. And without refinement, frame and segment alignment break down. So every component plays a crucial role in the final performance. Quantitatively, we evaluated on 5 standard benchmarks: breakfast, YTI, 50 salads, mid and eval, and desktop assembly. We report mean over frames, F1 score, and mean intersection over union. Across all datasets, key LOTs an average improvement of plus 2.5% in MOFON, plus 5% in F1, and plus 3% in MIOU over prior unsupervised methods, setting a new state-of-the-art. Here's a visual comparison. You can see that CLOT produces smoother, more consistent segments, especially for short actions. It reduces jitter and avoids over-segmentation. To summarize, first, our feature dispatching and sliced Wasserstein initialization help capture fine, underlying frame relations. Second, cyclic OT learning with multi-level refinement, using a parallel decoder and cross-attention, improves both frame and segment embeddings jointly. In short, we close the loop between representation learning and clustering. Thanks for your attention.